Okay, so we'll start with Abraham, that he will tell us all about what is the high frequency approximation.
All right, thanks. So in the schedule, I had a long and rather boring title, so I decided to simplify things and be a little bit more provocative and ask really this, I suppose, fundamental question that gets to the foundation of everything that we're talking about in one way or another. Although I'm only going to look at this, of course, in a particular perspective. What does it really mean to take a high-frequency approximation, and what do we lose in this approximation? Okay, so I'll start with the standard story. You open a textbook, and probably what you will find is some ansatz that looks like this. So let's say we're doing an electromagnetic case, and you say, let's suppose that we have a field, or really a one-parameter family of fields, because we have this large frequency-controlling parameter, omega. And we say we have something that looks locally like a plane wave, so we have e to the I omega times some function on space-time. So you take this as an ansatz, you plug it into Maxwell's equations, you expand in powers of 1 over the frequency, you take a limit as the frequency goes to infinity, and you get out a bunch of things. You get out all the nice rules of geometric optics, at least at leading order. So you find that there are rays. These rays are null geodesics. You find that the intensity of this field increases or decreases according to whether cross-sections of bundles are increasing or decreasing in area. You find polarization is parallel transported along your rays, and all of these nice rules that we use all the time. You can, of course, expand to higher orders as well and find other things. So Julia talked about this a little bit in her talk. And it gets quite complicated quite quickly, but this is the basic story. This is basically what a textbook will tell you is how you take a high-frequency limit. So as long as your wavelength basically is small compared to all relevant length scales in your system, the standard story is that this should be fine. And there's nothing wrong with that, a priori. But you can ask a question, which is, where does this ansatz come from? Why do I care about that particular form of a field? So does this thing actually show up generically? Generically meaning in a wide range of physical systems that we actually care about. Does it show up generically at high frequencies? And another question you could ask is, well, what is frequency anyway? So this is not always an obvious answer. And then what happens when you do this procedure is you get some expansion in, I'm going to call this frequency, even though I just said it, we don't know what frequency is yet. I'm going to call it frequency. Does expanding in powers of 1 over this thing, which is what you usually do when you take geometric optics and its perturbative corrections, does this miss anything? Does this miss anything in a qualitative sense? The answer, of course, is yes. Okay, so what do fields actually look like? So this is kind of an existence question. Do we actually care about this particular ansatz, WKB-like ansatz for a field? Well, let's start with something that we do know about a little bit more definitely. And this is taking a different perspective on things. So suppose that we, again, let's say we're doing electromagnetism. Same works in gravity, of course. And let's say we take our field equation and we introduce some Green's function g for it. So we have some P to E that this thing satisfies. Okay, our Green's function is sourced by a delta function, as usual. And then you could say, okay, without any real loss of generality, our electromagnetic field is given by integrating the Green's function against whatever currents you have in the universe. All right? That's what we should be seeing. And in gravity, of course, you would have a different Green's function, and you would have a stress energy tensor here. No. No. Arbitrary spacetime. Yeah. So the whole talk is arbitrary spacetimes. I'm not assuming flat backgrounds, weak gravity, stationarity, anything. Okay, okay. I'm assuming a linear field theory. So I'm assuming, okay, if you're doing gravity, it's linearized off of some background, but the background is arbitrary. Yeah. Okay, so we can have a Green's function here, and our fields are going to look like this. And this looks nothing like our WKB ansatz, at least at first. So how are these things connected? One should always have fields like this, but presumably, if the textbooks are reasonable, we should get back to the WKB kind of fields eventually. Right? So let's see how that happens. So we can compare these two approaches. So over here, our approach is, let's say, write down a Green's function and integrate against the source. And, well, you have to do something quite complicated here. You have to solve a partial differential equation to find the Green's function. That's difficult. Over on this side, using the sort of WKB approach, the standard approach, you write down this ansatz, and you end up just having to solve ordinary differential equations for amplitudes. This is enormously easier. right? And that's why we pretty much always just go to the left-hand side here and don't worry about what's on the right. Except in, let's say, non-lensing situations and other fields of other specializations in GR, let's say, one has to deal with this kind of thing all the time, and you can't go over to here. But let's try to compare these. It turns out it's interesting to actually bring together these two perspectives. But before doing that, let's compare a little bit these two approaches to trying to understand field propagation. So if you ask, okay, what kind of frequencies are allowed? If you take a Green's function approach, of course, this is completely general. You can have any frequencies that you want. From a WKB approach, of course, you usually want large frequencies in some sense. So this is a downside. It's an approximation. In the other direction, if you ask for simplicity, WKB is easy. Green's functions are hard. So you have your trade-off, as usual. Something else that's not, I think, mentioned quite as often as perhaps it should be, is if you want a connection between the fields that you're looking at and actual properties of the source, this is usually awkward in WKB. So if you want to somehow connect whatever you see to, let's say, in a gravitational case, let's say the quadrupole moment, time-varying quadrupole moment of the thing that is generating your metric perturbation, that's a little bit awkward in WKB. But of course, in a Green's function, you're integrating directly against the source. There's a direct connection there. Okay. Right. So let's say that we want to try to derive this WKB ansatz in however form it comes about. But we have to, and we want to do this at high frequencies, but we have to ask, what is a frequency? And let's say the usual way of doing this, or let's say the simplest naive way of doing this, is let's say you're in a flat background and you just, well, you can, let's say, Fourier transform with respect to a time coordinate or something like this. That also works in an obvious way in a stationary space-time. But in an operational sense, none of these things really matter, right? If you're an observer, you measure something that's a function of time, you can compute the frequency content of that thing, and you don't care what somebody on the other side of the galaxy is measuring for the spectrum of that same thing, right? All you care about is what you see locally. So you only care about your own notion of frequency, so your own notion of frequency with respect to your own proper time. Don't worry about the rest of the universe. Don't worry about defining frequencies away from yourself. So this is one possible notion of frequency. Just fix an observer and ask, what does that observer see? You can also do the other direction. You could say, all right, suppose you have a source. The source only cares about their own frequencies, the frequencies with respect to the source's proper time on the source's world line. And you could ask, okay, what happens in that context? What happens when those frequencies are large? And, well, in that case as well, the source doesn't care if it's being watched by someone from far away. Our source is not very shy. So we say, okay, our source only cares about its own frequencies. Don't worry about defining frequency away from the source world line. So this gives us sort of two different notions of high frequency limit that we can consider, because we can consider these two different types of frequencies. And in some cases, these things are basically the same, but in some cases, these really give you different perspectives. I want to talk about that. Okay. So I'll start with the what I'll call the observer-centered limit. And so the idea here is that we have some observer, and that observer is going to choose some observable. I'll call psi, so this could be a field. And we want to ask, okay, what is this field as a function of the observer's proper time? Okay, so you have to make that choice at the beginning. Then you just say, okay, this thing is a function of proper time. You can find its Fourier transform. It's a one-dimensional Fourier transform. There's no problem with that. You don't have to worry about the fact that you can't do Fourier transforms on space-time. You're doing a Fourier transform on a world line. That's perfectly well-defined, no matter what world line, no matter what space-time. Then you could just ask the question, okay, what is the high-frequency structure of this spectrum? So that's a simple question. And we don't need to define frequencies off the world line. That's what I'll call the observer-centered perspective. We can get something from that. We can also get something from what I'll call this source-centered high-frequency limit. So suppose that we have a source, and now we have to do something a little bit more. So we have to talk about some time-dependent property of this source, which is generating radiation. So for example, this could be some time-varying multipole moment, this Q. Okay? So fix some property, and then we could look at, okay, let's evaluate the Fourier transform of that property now on the source's world line. So this is now a source, a frequency measured with respect to the source. And you can say, okay, this thing here it sources a field, which is observed perhaps far away, and now you ask, how does this field depend on the high-frequency structure of the source's multipole moment? So in this case, we're asking for, in the observer-centered case, we're asking for something about a spectrum, which is observed, of some observable. And over here, so we're getting a Fourier transform of something. And over here, we're getting something that is in real space, right? This is a psi of x, that's a psi tilde of omega. And we're asking how this, in this case, how this real space observable depends on the spectrum of something else. So these are a little bit different perspectives. Okay, so let's start with the source-centered limit. This one's a little bit easier. So suppose we have some observer on this world line here, some source on this world line here. We have some observation point x. And whatever is being seen at that observation event, that depends on the entire past history of that event, right? And so you want to look at where does this light cone intersect the source? Well, it intersects the source all along this green line here. So in principle, whatever your observable is at x depends on everything along the green line. So it depends on this integral of whatever your source property q is integrated against your Green's function. All right. Now, what you can do is you can write your multipole moment here in terms of its Fourier transform and rearrange things a little bit. And when you do that, you have, instead of a time integral here, you have a frequency integral, right? And essentially what you're doing is you're shifting the Fourier transform from the source over to the Green's function. And this thing here is a kind of transfer function for your spacetime. I'll call it a source-centered transfer function. It's a little bit different from the normal transfer functions that people consider because you're not relating a frequency to a frequency. Here what you're doing is you are sort of relating, so you're sort of choosing a field point and you are, you're asking what happens when your source is oscillating at some particular frequency. How does that produce a field at the point x, a field in physical space at the point x? Okay, so you can ask now, how does this thing depend on, how does this thing behave at high frequencies? How does this transfer function behave? So okay, this thing is basically the Fourier transform of the Green's function evaluated on the source's world line, right? And the key point here is remembering something from mathematics, which is that if you want to know something about the high frequency behavior of a Fourier transform, well, how do you know that? That's basically asking you what is the singularity structure of the thing that you're transforming. So it's asking you how singular is the object that you're transforming, and how do those different singularities behave. So really what we want to do is we want to understand what are the singular parts of the Green's function evaluated on the source. And that will tell us the high frequency behavior of our transfer function. Okay, so what is the singular structure of a Green's function? Right, so we fix our source point x here, and then we're asking for what is the Green's function evaluated on some world line over here, the source's world line. And there's a general result that, at least if the space-time is sufficiently smooth, singularities will propagate only along null geodesics. Right? Even though you're solving a partial differential equation, there are general singularities on the general theorems on the propagation of singularities here. And so what you find is that there are singularities only along these path-directed null geodesics. And so you say, okay, there's a contribution basically from the source at this event, and so on. And these are exactly where you get the images of geometrical optics. In fact, what you find is that the high-frequency behavior comes from exactly these points where you find the geometric optics results. And you find at leading order, you get really normal geometric optics. You can also look at inverse powers of frequency, and you then find corrections to geometric optics. It turns out all of those corrections to geometric optics are still concentrated on just these 2 points, well, or as many points, as many images as you have. And you could ask, okay, what happens in between? So I'll talk about that more later on in the talk. But these are what are called tail effects, and these end up being non-perturbative in this 1/frequency expansion. So these are, let's say, exponentially suppressed. Those don't show up in WKB. Okay, right. So what is this transfer function? It turns out that this thing can be interpreted as basically the retarded field due to some oscillating source, some source that's oscillating with the frequency that you have in here. And you can do some expansions of things, and you find Well, the specific answer you have here depends on exactly what you choose for your observable and what you choose for your source function, for your source property. So here I have a scalar field and a monopole moment. If I ask for the gradient of the field, or if I ask for something more complicated, you get a more complicated expression here. But what you find is that you have everything here. This is of the form of a WKB series, right? We have e to the I omega something times a bunch of coefficients, where these coefficients are falling off with inverse powers of omega. And at leading order, we have 1 over the luminosity distance as our amplitude, and we have as our iconal, that's the retarded time function. So we can derive this WKB thing. And we have left over this tail here, which I won't talk about until later on. So we have something left over. Sorry, yeah. This. Yeah, so there's something called the Hadamard form for the Green's function in a general curve spacetime, and you can evaluate this, and you can essentially evaluate its Fourier transform, and you get this expression here. So you can evaluate the leading term explicitly. You get 1 over the luminosity distance, and the other terms involve basically derivatives of the Green's function as you approach the light cone. So yeah, this is generic. You have all terms in the series, in principle. Okay, so you have something that's of the form of this WKB series. So I'll just call this thing the WKB transfer function. So what do you have? To go back to what we had before, our field that we can observe far away is some integral of the Fourier transform of the source property times this WKB field. So what does that mean? That means, well, as one might expect, the fields that we see, at least within this approximation, at least where you ignore this tail term at the end, these are sums of these WKB fields. So the ansatz that we started with at the beginning, this is something that actually comes out. But we find it, of course, in general, we find a sum of those WKB fields that show up. So it's not just something pulled out of a hat, it is something that actually emerges generically. Okay. So there's some limitations to this. One of which is that I assumed I have a point source here. So I have some small coherent source. You might not want that. Of course, this is awkward at low frequencies, right? I have an integral over frequency here, and this TWKB here involves inverse powers of omega. That's completely nonsense at low frequencies. So you'd have to do some sort of high-pass filtering in here and so on, and that's just a mess. You can, of course, do it. The other thing here is that operationally, it's a little bit strange to expand in a source spectrum rather than an observer spectrum. An observer doesn't care what's happening at the source necessarily. They care about what they see. So let's consider the other perspective. Let's consider an observer, and they're looking at the high-frequency behavior of whatever they're measuring. That gives us the observer-centered perspective, this other kind of high-frequency limit. So here I can allow arbitrary sources. They can be extended sources. And I can say, all right, suppose that I now have my observable, again, on the observer's world line, and now I take the Fourier transform of that, so I'm looking at the spectrum of this observable, and this thing is going to be an integral of now the source, J, against some different transfer function. I'm calling it TO, so the observer-centered transfer function. This thing depends on basically a source point x prime and a frequency. So this thing ends up also being a Fourier transform of the Green's function, but a different, with a different arrangement of arguments, so a different Fourier transform. So this thing ends up being an advanced field rather than a retarded field. And basically, this thing looks like the field due to some source at the observer. Even though there's nothing physically radiating at the observer, one finds mathematically that it's useful to think about some fictitious source that is radiating at the observer and radiating backwards in time. Okay, so you find, again, you could do a high-frequency expansion of this guy. You again get a WKB field plus these tail effects. And you can say, all right, now your observed spectrum is going to be some sum of these WKB fields. But now I'm not saying fields are sums of WKB fields, not fields in real space-time, but I'm saying spectra are sums of WKB fields. So this is a little bit more subtle. But again, these two different perspectives, you can do these two different kinds of high-frequency expansions, and you find sort of sums of WKB fields showing up in either perspective. Okay, so let's compare these. So in the source-centered perspective, that assumes that you have a point-like source. It doesn't really pick for you a particular observer. You can easily move around your observer. Doesn't matter. From the observer-centered perspective, you're assuming you have a point-like observer, but you can have arbitrary sources. You can have extended sources. So sort of which one you pick here gives you more generality in one direction or another. And then you ask, how does WKB show up? Well, and from the source-centered perspective, it gives you, again, real fields are sums of WKB over frequency. From the observer-centered perspective, we find that observed spectra are sums of WKB summed up over source points in physical space. And in these cases, you have the iconals, which show up in the different WKB fields are, in one case, retarded time functions, in the other case, advanced time functions. All right. So what does this miss? It misses these things called tails. So tails are a wave effect. So tails are basically things where information propagates not only along null geodesics, but along time-like geodesics. So information propagates inside of light cones. If you imagine you have some experiment here where you have some source that sort of pops on and off like that, there's some sharp on and off behavior, and you could ask, okay, what does someone far away see for that behavior? If everything were nice and simple, you would say, okay, whatever the shape of this pulse is here, it would look like the same pulse over here. But if you have tails, this isn't true. So in fact, you find this black curve, that you find something that's going up, and it looks initially like the pulse that you started with, but then you have this long decaying thing at the end. So this is what happens generically in a curved spacetime. You have these tails. And you could say, okay, this is traveling along, this information is traveling along time-like curves, but to all orders, you can show that in the WKB series, your transport equations go only along null geodesics. You can never go in time-like directions. So how do you reconcile these two things? That you know from PDE theory that things move in time-like directions, but if you look at your WKB ansatz, it looks like nothing ever goes in a time-like direction. So how are these things compatible? And the answer is, well, your WKB series doesn't converge, basically. So really, it's an asymptotic series. I mean, most things in physics that we deal with are asymptotic series. That's fine. So it should be truncated at some finite order in 1 over frequency. And if you look at these things that are moving in time-like directions, well, these things are smooth, at least in most cases. And then if you look at the Fourier transform of something smooth, well, this thing is decaying faster than any polynomial in 1 over frequency. So however you truncate your WKB series, these tail contributions are going to be falling off even faster at high frequencies. These things are fully non-perturbative effects. They can never be captured, no matter to how high an order that you go. So an example of something which falls off faster than any polynomial is something that's exponential like this. This is giving you a little bit of perspective into where WKB comes from, but you also learn other things here. So by combining this Green's function approach and this WKB approach, you actually can understand new things. And one thing you can learn is you can compute these transfer functions explicitly. So I gave you one in a very simple case, but you get much more interesting things happening when you look at what are, let's say, how does the quadrupole moment of a source relate to the curvature perturbation of the gravitational waves? Right? You get something very much non-trivial there. And you also get various technical results that you can take sort of results from Green's function calculations that have been known by one community, results from WKB that have been known by other communities. These two communities basically don't talk to each other. You can have some communication now, and each side can learn something. So you end up getting technical improvements out of this. But I want to give one short application that I think is kind of fun. I'll call these metric invariance relations. And hopefully I can explain this quickly. This is a bit of a technical slide. Suppose that we have some geometric optics field in the usual sense, right? And we could split this into 3 pieces. So we could say, all right, there's our iconal up there. We have our amplitude A. And implicitly here, we also have some metric, right? So we say this thing satisfies all of the equations of geometric optics in that metric. And then I could ask, well, what happens if I change the metric? Right? You could say, OK, go back to first principles and just recompute everything and see what happens. But let's suppose that we don't do that. Let's say we choose a different metric in a particular way. And let's say we choose a different metric in a particular way that preserves the rays. So I won't get into what that means. But if you do this, it turns out this is basically still a solution. you can change the metric without changing the field, or at least you keep the iconal the same, you change the metric, and your amplitude changes at most by some local factor there. You don't have to solve any differential equations. So this is saying essentially that geometric optics transforms covariantly under certain transformations of the metric. And these are not very special transformations. In fact, you can transform arbitrarily 7 of your metric functions. So you have 10, let's say, components of your metric. You could do whatever you want to 7 of them, and these things stay the same. So this is a very powerful result. And you can use this now to try to understand how optical observables depend on the metric. What happens if, for example, so you have from this kind of calculation that 1 over the luminosity distance is a geometric optics amplitude. So this is not the first time that's been noticed, but you can, this is the simplest example. So okay, this luminosity distance is an affine distance over a square root of something called the Van Vleck determinant. Oops. And if you transform the metric in this particular way, well, that's saying that, okay, this amplitude is actually going to stay the same, or it's going to transform covariantly. And I'll just do a simple case here and say that actually these luminosity distances will basically stay the same under this huge class of metric transformations. There's some things that I left out here that I don't have time to get into, but basically you can transform non-trivial observables without going back to first principles. And the interesting thing is that this is not true for the affine distance. That does not transform nicely. The Van Vleck determinant does not transform nicely. The ratio does. You get to identify things that transform nicely under changes in the metric. And you can do this with advanced and retarded time functions. You can do this with redshifts. You can do this with all different kinds of things using this kind of method. All right. So just to conclude, you can consider different kinds of high-frequency limits. And of course, you can consider ones that I haven't talked about as well. But you can consider a high-frequency limit which is centered about the source, or centered about a source, I shouldn't say the source, a source, or centered around an observer. And these give you slightly different perspectives on what it is that you're computing, what it is that you mean. And if you have a stationary spacetime and all your world lines are stationary, then all these things are basically the same. But if we have a real situation where our spacetime is not stationary, our curves, our source and our world line are doing whatever they're doing, they're not doing anything simple, then these actually give you different information. Or let's say information that is not trivially transformed from one to the other. But whatever you do in this way, you do miss these tail effects if you do a high-frequency expansion. So those things are genuinely non-perturbative. So one thing that you get out of here that I haven't emphasized too much is that you have now these transfer functions that you can compute, and you have a direct relation between properties of the source and properties of the field that you see. That again, you don't usually have in a direct sense or in an easy sense when thinking about WKB. So you can compute these transfer functions with all kinds of observables and all kinds of source properties. This gives you some new technical improvements in different calculation methods. You understand new things about bitensors that are used to construct Green's functions. You understand some new things about objects in geometric optics as well. So you can leverage all of these things to then, for example, understand how luminosity distances and other things like that change when you change the metric. So there's lots of different applications of this kind of, let's say, marriage of Green's function techniques and WKB techniques.